Okay, so we're just going to pick up where we left off with hypothesis testing. We'll work through a few examples today. I'll introduce kind of some stuff with proportions. We will, as far as the exam goes, tentatively what I'm thinking, well, tentatively, this is what's 99.9% confident that this is going to happen. It'll be available Tuesday and Wednesday of next week, okay? So kind of similar to the last one, it'll be done through Canvas. I'll have some more specifics about the number of questions, short answer versus multiple choice, next class. But it'll be open those 2 days, and we'll still meet Tuesday, but I'll likely just be doing some review. So if you want to hold off until after Tuesday, it's probably the recommended. But just in case someone has a crazy schedule where they, I don't know, they'd have to take it Tuesday morning over those 2 days, although I doubt that's necessarily the case. That would be an option. So that's kind of where we're leading up to. We should get through hypothesis testing this week, work through a lot of examples on Thursday, and then do some review on Tuesday. I've got those exam reviews up on Canvas. So there's 2 practice exams. I'll probably also, if you start to see some additional videos get posted to the YouTube page, it'll probably be just me working through problems. So I mean, you have the answers and you have, I think on one of the practice exams, kind of how to work it out, but there'll be videos of me kind of working through those and explaining it as well if you kind of want to watch those as you get stuck on a problem or two, okay? Yeah, so hypothesis testing will be on the exam. You know, really hypothesis testing incorporates a lot of the concepts we've already talked about. It's just kind of putting them all together to be able to do something. Yep. All right, so let's go where we left off. So we left off last week kind of talking about p-values, right? How to find them. You know, once we calculate this test statistic, which is telling us the number of standard deviations away from that assumed true mean that our sample mean was, it's the probability of seeing that test statistic or anything more extreme, right? When I say more extreme, you can think about this as larger in absolute value. So if it's a negative test statistic, anything to the left, positive test statistic, anything to the right for a right-tailed test. And then for a two-tailed test, evidence on either side matters. So we mentioned that to find the p-value, we'll find kind of the area that's more extreme than our test statistic, but we have to multiply it by 2. Okay? And this kind of had it more formally written out. I think as we work through some more problems, just the procedure of finding the p-value will become a little bit more clear. And we'll work through several today. So kind of our steps. First of all, we got to figure out what the null and alternative hypothesis are. We talked about how we can do that because it matters if we have a left, right, or a two-tailed test. Okay? We're going to have to be comparing eventually our p-value to some alpha, so that's going to have to be set for us. So that's usually given in the problem. We then can take our sample mean, take the assumed true mean from the null hypothesis, create our test statistic. Once we have that test statistic, find the p-value. Once we have that p-value, compare it to alpha. If our p-value is less than alpha, we can reject. Remember, alpha was essentially this threshold we set where we said, if the probability of what we saw is anything less than 0.05 or less than a 5% chance of us seeing that, then we're okay rejecting our assumption. If it's not, right, if the probability is above 0.05, then we would fail to reject. Okay, so that was kind of our final step there. So let's go back to that example we were using. What we had was, if we go back far enough, we identified the null alternative here as being, well, what we want to test for, and let me, there we go. Switch the dot cam here so I can have this both pulled up. If it lets me do this. Might have to hit this real quick. Now let's see if we got this working. There we go. So we're looking at this example, and there we go. We said really what we want to test for is whether or not that true mean is less than 7%. So what we wanted to test for, that was our alternative hypothesis, what we're trying to find. What we do is then stack the deck against ourselves with the null, and we assume that the mean is in fact greater than or equal to 7, right? The complement of our alternative hypothesis. So what type of tailed test do we have? Well, we look at the alternative hypothesis, we see a less than sign. So we can think of, we've got a less than or a left-tailed test. Okay? That was something we kind of worked on last week. So we take a sample of 36 beers and we find an average ABV of 4.5. And let's assume for right now, in the problems we're going to be working through, we're given a population variance. So we're told, okay, this population variance is 1. The sample mean we found was what, 4.5, and our sample size was 36. Okay? And just as another thing, we were told kind of our alpha is that 5% level, or an alpha of 0.05. So how can we kind of determine whether or not we reject or fail to reject this null hypothesis, right? So we'll kind of work through the steps here together, put it all together. We kind of talked through them more generally, but here we've got all the numbers we would need. So what we're thinking about is if what we assume to be true is in fact true, that assumed true mean, the value we can use, the lowest value in this range is 7%. So if I find sample evidence that goes against the true mean being 7%, well then this is for sure going to go against it being 7.5 or 8.2 or any number above that, right? So we're going to use that assumed true mean that comes from our null hypothesis, which was 7%. Okay? We found a sample mean of 4.5. Right? That was our sample mean. So we're just plotting that. So the probability that we saw the sample mean that we did, or anything further from that assumed true mean, is going to be the area under the curve to the left of 4.5, right? This is the probability we saw 4.5, something that far away from the assumed true mean, or anything even further that went against the null, which is the definition of our p-value. The p-value is just a probability, and it's the probability we saw something from our sample as far away from that assumed true mean as we did, or anything even further that goes against that null hypothesis. So how can I find that area? Well, we know that if I have a normal distribution, right, which our sample mean should be normally distributed, we got a sample size over 30, I can turn any normal distribution into a standard normal distribution, right? How can I do that? So I want to turn this into a z-value, but because it's the statistic we're using to do this hypothesis test, we call it a Z statistic, or a test statistic that's coming from that standard normal distribution, or that Z table. And you know, once we have that Z value, I can look that up in our standard normal table and find the area to the left pretty easy. So how do I find this Z statistic? So just kind of a reminder, we looked at the equation last week, but all we're going to do is take that sample mean. Instead of subtracting the true mean, we don't have that, we subtract the assumed true mean, right? We were assuming that the mean was this value. We're then going to divide by, and what's going to be in our denominator here is the standard deviation of the statistic that we're looking at, the sample mean. Well, what equation do we know calculates this? This is kind of like with confidence intervals. We said we can always calculate the intermediate step, which is to think about what that standard deviation was on our distribution of sample means. So this was just what? The square root of the original variance we sampled from over our sample size. Like this goes all the way back to thinking about when we were just looking at that birth data, right? Just the distribution of sample means. It's the same concept. It's the same idea. So here we've got what? The square root of, this is kind of easy, 1 over 36, right? So I could actually, if I wanted to, plug this all in down here in the denominator. I could do this all as one step, or I could calculate it first and then plug it into my denominator, right? Either way, it's kind of the same, it's gonna give me the same values, okay? So, you know, I plug everything in here and I get what? 4.5 minus 7 over the square root of 1 over 36. That should give me my Z statistic, okay? Now it's a test statistic, but it's coming from that standard normal distribution. It's still a Z value. It tells me the number of standard deviations away from the assumed true mean, what I saw from my sample was. So I go ahead and I plug this into my calculator. I think I get negative 15. I'm keeping my examples correct here. Now, right away, if I see a Z value of negative 15, hopefully kind of up this point, we're starting to realize that's a pretty wild value, right? To see something that's 15 standard deviations away from the assumed true mean, if we go to our, and I'll come back to this in a second, if we go to our standard normal table, I mean, the area to the left of negative 3.9 is 0. Well, it's not technically 0, but to the fourth decimal, it looks like 0. It's so small. So if I have a test statistic of negative 15, even further out into that tail, the area to the left of negative 15 is going to be even closer to 0, right? So when I find this test statistic of negative 15, right, I know that area to the left represents my p-value. And if the area to the left of negative 3.9 is pretty much 0, the area to the left of negative 15 is going to be approximately 0. Right? So this was kind of an easy one. And it kind of makes sense, right? I mean, we saw a value that was pretty far from that assumed true mean. So what's more likely to be true? Well, first of all, are we okay with this up to this point? Are there any questions before I kind of continue here? Okay. Yeah.
I think there's one thing that I'm a little unsure about. You were saying because it's negative 15, if the p-value less than 4.5 is close to 0, then negative 15 definitely will be. Is that what you're saying?
Sorry. Yep, good question. Okay, so remember, here, this distribution, we're looking at my sample mean value. We then converted that into z values. So what I was saying, I can get this, there we go. If I'm looking at a standard normal distribution, and I looked up that value of negative 3.9 on the table, the area to the left was like, I don't know, I'll make up a number. It's something like that. It's really, really close to 0. So if I have a test statistic, which is a z value, right, of negative 15, the area to the left of that is just going to be even closer to 0. Yep.
Okay, I got it. Thank you.
Yep. Okay. So it's so far away from that assumed true mean. That's what's probably more likely is that the true mean is somewhere over here. So like, let's say I assume that the mean is greater than or equal to, I don't know, 5. Well, then I'd end up with a p-value that's a lot higher, and I probably wouldn't reject the null, right? But given the scenario we have, if the p-value is 0, and we only reject when that p-value is less than alpha, if my p-value is approximately 0, can I reject an alpha of 0.05, or can I reject if the alpha is set to 0.05? Well, yeah, 0 is going to be less than 0.05. In fact, I could set alpha to just about as small as I want, and I'm still going to be rejecting here because my p-value is so close to 0. I found really strong evidence to suggest that this isn't the true mean. What I assumed to be true wasn't true based off of what I saw from my sample. Okay. Any questions on that before we keep moving? So one thing that I skipped last week, but we want to come back to, and here I've kind of have everything worked out as well, what we just did by hand if you want to kind of use this as a reference. Well, yeah, sorry, I'm jumping ahead. We'll work through another example before we get to the discussion of type 1, type 2 errors. So let's say we'll work through another example where we have a sociologist and he wants to test for whether the mean retirement age is what? Greater than 67? So right away, first step, identify our null and alternative hypothesis. What we want to test for is our alternative hypothesis. And what we're trying to test is that true mean greater than 67? So that's your first step. I think reading the problem, if you want to test for this, you just identified your alternative hypothesis. Next step, okay, well, if I know the alternative hypothesis, the null is just the exact opposite of that, or the complement, so we assume that true mean is less than or equal to 67. Okay. The other, I'll move my mouse there. The other information we're given, what? We find a sample mean of 71 from a sample of 25 individuals. And we were told that the population variance is 81 here. Now, I didn't give you an alpha here because I'm not asking what the outcome of the test is, right? I'm going to save that for after the fact, and I'll kind of show you why. But here, all I'm asking you to do is find the p-value. You don't need alpha to find the p-value. The only reason why you need alpha, and that's, like I said, something that's going to be given to you, is so you can compare your p-value to it. So I can think about, all right, I've got my null hypothesis. If that in fact is true, my sample mean should be normally distributed around that value of 67, right? Now, when I eventually do this, if I can reject 67, then I can reject anything below 67 as well. Think about it this way. If I'm telling you, okay, assume the true mean is 67, you see a sample mean of 71. If you can reject 67, well then, if the true mean was 65, seeing 71 would just be even less likely, right? So for sure, if I can reject 67, I can reject anything below it because that would just make what I saw even less likely. So we know that it should be distributed around that assumed true mean, normally around it. We see a sample mean of 71. Now notice, one thing I didn't do here, just is kind of identify the type of test. Before, we had a less than sign in the alternative hypothesis, so we had a left-tailed, or a less than or a left-tailed test. Now we've got a greater than sign, so we can kind of think about this as a greater than, or, oh, sorry, what?
Sorry, I thought you were asking.
Yeah. No, good. So greater than or right tail test, right? No, good, yeah. If you know, you can speak over me if you can beat me to it. So we've got a right tail test because only values on the right side of 67 would go against that null. Okay? So I'm thinking about the probability I saw something as far away from that assumed true mean as I did, or something even further away that goes against the null. Well, that's the definition of my p-value. It's just now it's on the other side of the distribution, right? Because now values to the right are what goes against my null hypothesis, or said differently, what supports the alternative. Okay? Well, from here, I could have calculated an intermediate value here, which is the standard deviation of my sample means. We said that's just the square root of the original variance over my sample size. So square root of what? 81 over 25. I've got a normal distribution. Let's just make this bigger now that we're done with all the information. So I've got a normal distribution. I can turn it into a standard normal distribution by calculating my test statistic, or my Z statistic here. And then, right, my p-value is going to be the area to the right. Okay? So how do I do that? Well, we had the equation already right here. Right? So all I'm going to do is plug in my sample mean minus that assumed true mean. So what? 71 minus 67. And I'm dividing by my standard deviation of my sample means, which I've already calculated. So if I had this number, I could just plug it into my denominator. Or because I don't have a calculator in front of me, and I think this is, I think it's going to be 9/5. So you could plug 9/5 down into here, or you could do it all at one time and just plug in the square root of 81 over 25. Right? Because this denominator represented that standard deviation of your sample means. If you do that, I believe you get 2.2. I think it's 2.22. We'll see. I might be wrong on this. Any questions on this up to this point? So we just found our test statistic. Okay. So the next step, we've got to find our p-value, right? So we got to look up 2.22. So here's the second decimal, 2.22, 0.9868. Now we have to remember the right-tailed test is a little bit trickier because I just found the area to the left of my test statistic, right? I wanted the area to the right, so I have to subtract that from 1, right? So you get what, 0.0132 here, I think? Any questions on that? Now, okay, first of all, I was making so there's no questions on that before I say this next thing. Okay. if it's easier, I don't want to complicate it, but because I know this is a symmetric distribution, if this 1 minus kind of trips you up with a right-tailed test, if I looked up negative 2.22, what value would I find to the left of it? Remember, my standard normal distribution is centered around 0, and it's symmetric. So if I folded this in half, the area to the left of negative 2.22 would just be 0.0132. Right? I can actually confirm that to myself. Oh, come on. Full screen. There we go. If I go to that standard normal table, and I look up negative 2.22, 0.0132, because this is a symmetric distribution. I think usually it's if you have a really good understanding of kind of what's going on with hypothesis testing, that makes sense. If you're still kind of uncertain, then it's fine to just think about it with the picture, right? Because the picture, if you draw it out, will always remind you, you want the area to the right, the table gives you the area to the left, you still have to subtract that from 1. Just kind of whatever is easier for you. But I think with the, drawing the picture, I think is, especially starting out, always makes it a little bit easier. Okay? Yeah.
Could you do something like the triple stuff on the test and put like 0.9868?
Probably. Right? Because it's an important, and this is why the visual helps, because it is important that, if I'm trying to come up with a decision here, a p-value of 0.0132 and 0.98, wildly different. So if I'm making decisions with that p-value, I need to make sure that I know what I'm looking at, and a p-value of 0.98 is also really ridiculous, in the sense that most of the p-values we see are going to be somewhere between 0 and 0.5. To see something of 0.98, I don't think we'll get there today, but Thursday I'll show you an example where that would actually be something that supports the null, right? Because it was so likely that I saw it, right? The probability I saw it was 98%. Well, that's got to be something that's supporting the null then, so that we won't ever really see p-values there, because we'll just look at the sample mean and say, well, if I see a sample mean of 65, well, that supports the null. I'm not going to go through the whole process. I already know that I'm going to fail to reject it, right? But yeah, that's kind of an important step there if we're doing a right-tailed test. All right. So we'll use that p-value. I want to kind of discuss something here. So my p-value is 0.0132. Right? I only reject if my p-value is less than alpha, right? This was the only scenario in which I reject. So in these problems, sometimes I'm given one specific alpha value that I'm testing against, or kind of doing my hypothesis test at, but I can compare to multiple alphas real quickly, because the process of finding the p-value is going to be the same every single time. So all I have to do is say, okay, look, is that p-value less than 0.1? Well, yeah, it is. So I can reject, and we'll talk about this here in a second. 0.1 is I can reject at the 10% significance level. Or think about it differently. It's like confidence intervals. If the significance level is 10%, my confidence level is 90%. Is my p-value less than 0.05? Yeah, so I can reject at the 5% significance level, or reject with 95% confidence. Can I reject at an alpha of 0.01? Well, I'm just barely not less than 0.01, right? So I would fail to reject here at the 1% significance level, or fail to reject at the 99% confidence level. Okay. So, this kind of highlights, once I have the p-value, I can test against any alpha you throw at me very easily, right? As long as I can see whether or not one value is less than the other or not. Okay. Any questions on this before we keep moving? All right. So I think I got one more example, because up to this point, and I kind of have some of our work here. Up to this point, we looked at a left-tailed test, a right-tailed test. The only one I haven't done yet is a two-tailed test, right? So, it's really the same steps, right? But what we're going to do is, I kind of already cheated and told you that we're going to have a two-tailed test, but if I read a problem like this where, okay, so some trade group says back to school spending averages $606.40. A researcher doesn't really believe that, and they think that the true value differs from this amount. So one thing I said on Thursday was anytime we see this kind of terminology of like different than or differs from, what we're saying is we don't think that it's equal to this amount. So our alternative hypothesis, what we're trying to find, is that that true mean is different or not equal to that reported amount of $606. So we stack the deck against ourselves with our null hypothesis and assume that that reported value is in fact the true mean. Okay? So we identified the alternative. Kind of one of the key is anytime we see this like differs from or different than, we should be thinking a two-tailed test or a not equal to test, not equal to sign the alternative hypothesis. We then get what? Sample size of 30, sample mean of 622.85, and we're told the population variance is 4,225. So I'm just writing down there what we were given in the problem so that when I shut the screen off and go to just the .chem, we've got everything laid out in front of us. Okay? Once again, I just want to find the p-value here. So if I want the p-value, which of these can I rule out? Remember, the p-value represents a probability. A makes absolutely no sense, right? Kind of from what we talked about earlier, B probably doesn't make a lot of sense because to see a p-value as high as 0.9, that's probably going to be something that supports the null. Well, here we see a value that is a decent amount away from that assumed true value, so probably not as likely of us seeing as 90% or whatever, 91%. So let's just actually work through everything though. So with this information, we can think about the distribution of our sample means should be normally distributed around that assumed true value of $606.40. Okay. We found a sample mean value of $622.85. So this is where it gets a little tricky. With a two-tailed test, the p-value's definition is the probability that I saw something as far away from that assumed true mean as I did, or anything even further that goes against the null hypothesis. But if that's the definition, I didn't give a direction there, right? I just said if it's as far away and goes against the null. Well, now with a two-tailed test, if I had seen a sample mean equally as far away on this side, right? So I don't know what, this is like about 590. If I would have seen 590, it would have been equally as likely for me to see these sample means, and all of these now go against that null hypothesis. Before, when I'm looking at the other side of the distribution, you know, what's the probability I saw something as far away from the sample mean as I did, or even more? Well, I could have seen something over here, but the last part of the p-value definition is that goes against the null. Well, now if I see values over here, that supports the null. So for a right-tailed test, my p-value was only the area kind of in that tail. With a two-tailed test, evidence on either side would have went against the null because the null is just that it's exactly one value. So I can turn that sample mean value that I found into a Z statistic. I can use that to find the area to the right, but this is only going to be half my p-value because it would have been equally as likely for me to see something on the other side that also went against my null. Okay. But the steps are the same, right? So I'm going to calculate my Z statistic. So all I do there is take my sample mean and I'll subtract the assumed true mean and I'll cut out the intermediate step and just plug into the denominator the square root of the original variance over the sample size. Just as a reminder, this represented our standard deviation or sample mean. So here I saw what, 622.85 minus 606.40. It's a minus sign. And then divide by the square root of 4,225 over that sample size of 30. Okay. Any questions up to that point? Okay. So if I get this entered into my calculator, I believe this is 1.39. It's in the slides. If I'm a little off here, it might be a little slight different, but I think it's 1.39. So what I'm going to do, actually, let's just double check my memory. There we go. Yep. So 1.39. I can look that value up in the table. So scroll down here. 1.39, 0.9177. Okay. So 0.9177 is the area to the left of 1.39. Okay. Well, I need the area in the tail. So what I was just told was the area to the left of 1.39 is 0.9177. I wanted the area to the right, so 1 minus that. But now that only represents half of my p-value, so to get my total p-value, I still need to then, for a two-tailed test, multiply it by 2, right? Because I've got two tails on either side that are the same size. Okay, so I think if I do this, I get approximately 0.16. Okay, so pretty high p-value. You know, once I have the p-value, I can start to think about, can I make rejections at different levels? All right. So I've got kind of a synopsis of these two examples. So example 2, we found the p-value. I guess the exact one is 0.1646. I chose some different alphas here just to make this a little more interesting and highlight that I can reject and fail to reject at different levels. So notice for example 1, we said, or sorry, we did the 0.1, so we can reject at 0.1, but not at 0.01. For example 2, well, our p-value is 0.16. That's less than 0.2, so we could reject at the 20% significance level or reject with 80% confidence. But if we look at kind of our more conventional benchmark values, the alpha of 0.1, we're not less than 0.1 here. In fact, we're greater. So we fail to reject at that 10% significance level, or we fail to reject with 90% confidence. And then if we're less, you know, if we're greater than 0.1, we're definitely not going to be less than 0.01, so we fail to reject at that level as well. So, you know, the same example, finding the same p-value, your rejection decision is going to depend on what level you want to reject at. The lower the alpha, the more difficult it's going to be to reject the null, right? Because essentially what it's saying is, with a lower alpha, you need to be able to say something with a higher level of confidence. And that's harder to do, so it just makes it harder to reject the null. Just making sure that it was on the screen and not the dot cam as I'm just talking away. Any questions on kind of that comparison, making the rejection decision? Any other kind of question you can have at this point? Okay. So hopefully we're getting a little bit more comfortable kind of with the procedures of this hypothesis test. But one thing I want to go back and mention is the idea of type 1 and type 2 errors. So type 1 errors would be if I reject the null, and then after the fact I find out it was actually true, right? So I made the wrong decision. I rejected when I shouldn't have. Type 2 is if I failed to reject the null when in fact I should have, right? I end up finding out that assumed true value wasn't right. So we have these type 1 and type 2 errors. You can kind of think about the correct decisions are, well, if I fail to reject and it's true, I was right. Or if I reject and it ends up being false, then I was right there as well. The kind of different combinations of those two things would be our type 1 and type 2 errors. Now, the reason why, hold on. So these type 1 errors, another way we can reference them is alpha, right? So this alpha that we're using really represents the type 1 errors that we're going to make. So why does this represent kind of the proportion of the time we'll be making a rejecting when we shouldn't be? Okay, so let's say we have some example, and I don't know, we've got this assumed true mean. Okay, I know that if I see, I want to set this up here. draw this to explain it. Let's say this was 1.65. So I'll kind of help you out here, but if I look at that standard normal distribution, if I see a z value of negative 1.65, so if my test statistic was 1.65, the area to the left of it would be 0.05. Right? So I can think about, if I could work backwards, kind of using that inverse transformation formula, I can find like a cutoff sample mean value such that if I see any sample mean that was this far away from that assumed true mean or anything further away, that's all going to turn into a test statistic that's going to be out here and give me a p-value or an area in the tail that's less than 0.05. So there is some cutoff value. Depending on the example, I don't know what that would be, right? But I know that the z statistic for that cutoff value would be negative 1.65, just based off what I know about the standard normal distribution. So let's say we go through this hypothesis testing. If I saw any value out here, I'm going to end up with, so like let's say, for example, I see this is my sample mean. Here's my test statistic. The area to the left of it is my p-value. It's going to be something smaller than 0.05, so I reject, right? So any sample mean I see out here, I'll be rejecting, right? Now let's say I do a hypothesis test and I end up, maybe I do some hypothetical where I just take like an infinite number of samples, right? And I make a reject, for every single sample, I just see if I can reject or fail to reject this assumed true value. Then I look at all those, infinite number of samples, what proportion of them, right, would have been correct and what proportion of them would have been false if I find out that the true mean is in fact what I assume to be true. So if what I assume to be true was in fact true, every time I saw a sample mean out here, I would have been rejecting when I shouldn't have been. And that I was kind of okay with that ahead of the time because I was saying, well, look, everything out here, the probability I see something out here, it's going to be less than 0.05. It's a very unlikely event for me to see a sample mean all the way out here if this in fact is true. So even if it ends up being true and I did reject here, I was okay with that. I was going to be wrong 5% of the time, or the probability I was wrong was alpha, 0.05, right? I guess I can kind of, right? We were thinking about alpha as being 0.05 there, which means I would have been correct, right? 95% of the time, okay? So, or the probability I was correct would be 0.95. So when we're setting this type 1 error, when we're setting alpha, what we're really saying is even if what we're assuming to be true is in fact true, I know I'm still going to be making the wrong rejection decision some of the time. And how comfortable, like what level of comfortability do I have? Am I okay making errors 5% of the time? Am I okay making errors 10% of the time, right? And that's really what I'm doing when I'm setting alpha. I'm setting the number of type 1 errors I'd be making if what I assume to be true was in fact true. Any questions on that? And you don't have to have a perfect understanding of kind of these like what's going on with the type 1, other than like we're always going to be setting that type 1 error that we want, and that what that is alpha, right? The alpha that we're going to be comparing our p-value to. All right. So I saw this as an easy example, right? If the null hypothesis that is someone is not pregnant, type 1 error would be saying, okay, I reject that, even though clearly I shouldn't have been. Type 2 error would be if I fail to reject that null when clearly I should have been, right? So we've got our type 1, type 2 errors. I kind of already walked through this. I'll hold off on type 2 errors. We'll probably go a little bit more in depth into this after the exam. So we'll hold off on type 2 error discussion, but just know that it's somewhat related to the type 1 error we choose. But like I said, we'll spend more time on this after the exam. And I've kind of already started using this terminology, but when we're talking about our benchmark alphas, 0.1, 0.05, and 0.01 are usually the ones that we're going to use to do these hypothesis tests. We always kind of can say these as the 10, 5, and 1% significance levels. That's another way that we reference them. All right, so, and then I always like this. So I made a type 1 error. I shouldn't have rejected you, right? Because type 1 errors, you reject someone when you, okay. Anyway, so we're running low on time this week. So we got a little bit of time left today, though. And I want to introduce 2 other ideas, but I want to make sure that it's clear that they aren't tied together. So we just worked through examples where we were doing hypothesis testing for where the true population mean was using the p-value approach. Another approach we have is called the critical value approach. And we can also do hypothesis testing for population proportions. So some of the examples we'll look at, they're going to be proportion examples where we're using the critical value approach, but I could have used the p-value approach, right? I'm just using these examples to introduce to you how we could work through the critical value approach. And by the end of class, hopefully, I'll have kind of shown you that it doesn't matter which approach you use, you end up with the same rejection decision, okay? So let's get the easy part out of the way, which is we can do hypothesis testing for proportions. It's not going to be a lot different, right? You know, we've got our null alternative hypothesis. We've got 3 different types of tests. The only difference from the slide that I showed you on Thursday to this is instead of means, we've got proportions, right? So I will still choose kind of this null hypothesis where I'm saying it's, you know, either greater than, you know, 0.6 or less than 0.4, right? I'll kind of have this assumed true population proportion, and then I have the same 3 types of tests. Greater than sign in my alternative hypothesis, greater than our right-tailed test. Less than sign in the alternative hypothesis, less than or left-tailed. Not equal to sign in an alternative hypothesis, 2-tailed test. And all the principles apply the same. So when I'm looking at the steps here, first 3 steps are these steps, oh, sorry, I wrote these out for the critical value. So if I go back here, where did I have the steps earlier? 3rd slide. There you go. Every step is going to be exactly the same, but when we go to calculate our test statistic, it's going to look a little bit different. Okay? So I don't have to give anybody a seizure as I'm scrolling through these. Where were we at? We were right here. Right. So when we go to calculate that test statistic, it's going to look a little bit different than when we're looking at a population mean. Okay? So I'll explain to you exactly why this is what it is. So let's go to the .cam, and I'll have that formula up again if you're kind of writing things down. But we're going to construct it. Okay? So before, when we wanted our Z statistic or our test statistic, we took sample mean minus assumed true mean divided by standard deviation of our population variance over our sample size, where that denominator represented the standard deviation of our sample mean. We're going to do the exact same thing with sample proportions, but not using a sample mean, I'm using a sample proportion. Instead of an assumed true mean, assumed true proportion. And then when we want to divide by the standard deviation of our sample proportions, this is where what we did with confidence intervals doesn't completely translate to hypothesis testing. And the reason why is because we said for confidence intervals, we know what the true standard deviation of my sample proportion should be is this. The problem was when we did confidence intervals, we didn't have the true population mean. So what did we do? We used our best guess, which was our sample proportion. Well, now, instead of using our sample proportion to calculate that standard deviation of our sample proportions, we have something better. We don't have the true, right? What we wanted here was the true population proportion, but what we have is the assumed true population proportion. So we'll just use that instead, right? It's really similar to what we did for confidence intervals, but now instead of kind of using this estimate of what the standard deviation of my sample proportions is, I use what, to calculate that, I use that assumed true population proportion there. But notice the setup of these test statistics are all the same. When we're calculating these Z values, take the statistic you're interested in, subtract the assumed true value of that statistic, divide by that statistic's standard deviation. It's just finding the standard deviations are a little bit different when we're looking at means compared to proportions. Okay. Any questions on that before we keep moving? So, you know, now that you have this test statistic equation, you could really work on proportion examples using the p-value approach exactly the same as we did for means. It's just slightly different test statistic equation. But in terms of once I have that test statistic, look it up in the table, find the area to the left for a left-tailed test, area to the right for a right-tailed test, two-tailed test, you'll find the area in one tail, multiply it by 2. Although that, you know, it's the exact same setup as what we were doing before. Just a small, small wrinkle, which is that the test statistic equation is a little bit different. Okay. Okay with that? All right. So the next idea that I'm going to kind of mesh into these proportion examples is instead of using the p-value approach, we're going to use the critical value approach. Okay. So we kind of have some formal setup of this here, but I think I'm just going to draw some stuff out that I think helps give us slightly better idea of what we're doing with the critical values. So with the critical value approach, what we're going to try to do is say, okay, look, we're actually going to start off thinking about that standard normal distribution. Okay. So let's say I've got this standard normal distribution, and for the sake of what we're going to do, we're going to start out with a left-tail test. Okay. So let's say that I have an alpha set at, let's use 0.10. Okay. So what I can think about is, I know that there is a value, a z value, that corresponds to having an area of alpha total in this left tail. Right? It's basically working in reverse or inverse, right? If the alpha that I want is 0.1, well, what would I do? I would go to my table and say, look, I now know the area I want in my tail. So I'm going to scroll, I'm going to try to find 0.1. Looks like it's in between these two values. So negative 1.28 and negative 1.29. Kind of just like with confidence intervals, we'll take the higher of the two. Right? So I can kind of think about that critical value that would give me 0.1 in the tail would be negative 1.29. Okay? That's how I would look up that critical value. But the broader idea with critical values is I'm saying, look, I know that if I see a test statistic that's negative 1.29 standard deviations, so let's kind of remember, we can map these back out to the distribution of our sample means, where they would be distributed around the assumed, oh, not mean, sorry, our sample proportions, because we're talking about proportions now. So they'd be distributed around that assumed true proportion. And there is some proportion that if I see a sample proportion here that's negative 1.29 standard deviations below that assumed true population proportion, the probability I see something 1.29 standard deviations below this value is alpha, or is 0.1 in this example. Okay? So now the idea is, okay, if I see a sample proportion anywhere out here, really, that's going to translate to a test statistic that is more, represents more than 1.29 standard deviations away from that assumed true value. And if I calculate the p-value, hopefully you can do a little better job than I did, right? Well, that area to the left of any test statistic in this range is going to be a p-value that's less than alpha. So really what we're doing is comparing two sides or different sides of the same coin, right? Before with the p-value approach, I was saying, okay, if my p-value is less than alpha, I reject, right? But in order for my p-value to be less than alpha, I would have to have a test statistic that's more extreme than my critical value. So the idea is once we look up this critical value, I can think about my rejection region will be as if I see any test statistic more extreme or larger in absolute value, I know that's going to lead to a p-value that's smaller than alpha. So instead of finding the p-value in alpha, all I have to really do is compare, oh, I'm knocking my papers over. All I have to say is the absolute value of my critical value If it's less than the absolute value of my test statistic, then I'll reject, right? Or said differently, if the absolute value of my test statistic is larger than the absolute value of my critical value, I'll be in that rejection region, so I would reject. So, here we're comparing the area and the tail for the p-value approach, and we're just going to be comparing the z-values in the critical value approach. And the reason we can do that is because those same z-values will always correspond to the same areas in the left tail, right? So it doesn't matter which ones I choose, right? If I have a smaller area in the tail, I know that's going to be a larger z-value, or larger in absolute value, because we're dealing with negative values here. But so it's really just comparing areas in the tail versus values on the x-axis. And I think the one thing about the critical value approach is I think it translates to being a little more intuitive, because really what I'm saying here is if I want to be able to reject that assumed true proportion at a 10% significance level, I'm going to have to see something. I'm going to have to see a sample proportion that's more than 1.29 standard deviations below that assumed true value. Well, the Z statistic, my test statistic, tells me the number of standard deviations below I am. So if I see anything more than 1.29 standard deviations away, I can reject it. So instead of setting my threshold probability, I'm setting my threshold number of standard deviations away, which are really the same thing. Like if I know one, I can automatically know the other because I have that standard normal distribution table, but it's just going about it a little bit differently. Questions on that before we kind of start to try to apply this to a problem? I know these concepts I know this is tough. This is not lost to me. So if you have questions, we want to make sure we get these out of the way. Okay. And I don't know if I'll get there today. I might start off next class with it, but because I think I'm going to just work through some problems and show you the critical value approach. But we can really do either approach for these problems and show that they give us the same answers. Oh, like I said, it depends on how the examples are going. So we'll see. Okay, so we've got this idea of critical values. This is where, to make general statements, it becomes a little bit trickier with critical values. So I've got all this lined up. If you don't think about it as the absolute value, it starts to get tricky because if it's a left-tailed test, my test statistic actually has to be less, but if it's a right-tailed test, if it's greater, if it's a two-tailed test, so I could be looking at either side. So if we're really trying to write this out, the easiest way to do it is what I have here. If you just ignore the signs, if you always just look at the absolute values, if your test statistic is larger in absolute value than your critical value, you reject. If it's not, you fail to reject. It's also probably easier if you draw these out because, I can literally draw, right, with this arrow, a rejection region, right? If I see any test statistic in this region, I reject. If I see a test statistic out here, right, I fail to reject. So it's not in the rejection region. The visual makes this a little bit easier. But if we don't use the absolute value, now it depends on what type of tailed test we have. So I would just always kind of default to that. So what is that going to lead to? Well, before we look at this slide, we had a left-tailed test here. And if I wanted an alpha of 0.1 in that lower left tail, I had a negative critical value. And in fact, I know that for my critical values of typical alphas of 0.1, 0.05, and 0.01, what would my critical value be if I set, and I'll start drawing it out, we'll see if anyone can beat me. What would my critical value be if I wanted an alpha of 0.5? So if I wanted an area of 0.5, the z value that would give that to me, the area to the left, would be what? Remember, this is a symmetric distribution, so there's 50% of the data to the left and the right of the mean. So if I did want an alpha of 0.5, right, I wanted this area to be 0.5, what would my critical value be? My critical value is coming from, so one thing I want to be clear on here, my critical value is a z value, right? It's coming from that standard normal distribution. So what z value would give me 0.5 to the left? Well, what's the mean of my standard normal distribution? Someone said it, 0, right? So when I'm dealing with alphas of 0.1, 0.05, and 0.01, in order to get that, my critical values are going to have to be further into the left tail, or anything to the left of my mean would be, right, negative, right? So you can kind of think about it as, for a left tail test, all my critical values will be negative. Well, what about for a right tail test? Well, a right tail test, I'm looking for the critical value that gives me alpha in the tail, but now alpha in the tail is that upper right tail. So if there's 0.1 in the upper right tail, what's the area to the left? Area in the curve is 1, so the area to the left would be, the area to the right here is 0.1. The area to the left has to be, yeah, 0.9, right? So in order to get 0.9 to the left, I'm going to have to be using a critical value that is above 0 or positive. So for my right tail test, I'll have positive critical values. For my left tail test, I'll have negative critical values, but it's a symmetric distribution. So before, when we said if I wanted an alpha of 0.1 in the lower left tail, that was a negative 1.29. So if I want 0.9 in the upper right tail, my critical value is going to be positive 1.29. So, you know, when we do this in practice with a right tail test to find my critical value, instead of thinking about this as, okay, the area I want in the upper tail is 0.1, okay, 1 minus that, the area to the left would be 0.9, I'll look up 0.9. Honestly, that's fine, but an easier way to do this to me is, whatever your alpha is, just look that up. So I'll look up 0.1, we'll find the same thing we did before, which was, oops, it's in between 1.28 and 1.29. Well, this is saying that it's negative because I just looked up alpha, right? I just looked up that area, and the table is always the area in the left tail. Well, if I know negative 1.29 gives me 0.1 in the left tail, I know positive 1.29 gives me 0.1 in the right tail. So I can just look up alpha and remember, for a right tail test, it's that value, but positive, right? So if we go and look at this table that I had, and we'll kind of ignore this for a second, these different alpha values, I'm always going to find the same z values, give me the same desired areas in the tail. And notice for a right tail test, they're positive. For a left tail test, it's those values, but negative. Okay. Any questions on that? And we're going to, it's about two-tail tests. Hold off. I'm going there right afterwards. So two-tail tests are a little bit trickier in that when I'm thinking about alpha, the probability I make a type 1 error, what I have to think about is, okay, I need the z value that gives me alpha total in my tails. So I need to find the z value, which is going to represent our critical value, that gives me alpha over 2 in each tail. So this goes back to very similar to confidence intervals. Remember when we were getting those z values to build our confidence intervals? Those z values will actually end up being exactly what our critical values are equal to, right? Because it's the same idea. It's what z value gives us alpha over 2 in each tail. Now, they'll be the same value, but one will be positive, one will be negative. So for every alpha, at a two-tail test, we'll have a pair of critical values, right? So think about it here. If we wanted alpha to be 0.1, alpha is the total area in the tails. So actually, the way I sometimes say to think about alpha, right? It's either the area in the tail if you have a one-tail test, or it's the area in the tails if you have a two-tail test. So 0.1 over 2, 0.05. So now when we go to our standard normal table, trying to find 0.05, it looks like we're in between these two. So negative 1.6, scroll up. Negative 1.64 and negative 1.65. We use the higher of the two. So negative 1.65, but also positive 1.65. So the way that we'll typically write two-tailed test critical values looks like this. Okay? We have to indicate that 1.65 is that Z value, right? That would give us alpha total in the tails. However, because we have two tails, we need kind of two cutoff values here, which would be 1.65 and negative 1.65. Okay. So two-tailed tests, when we're finding critical values, it's really like identical to what we were doing when we were trying to find the Z value for our confidence intervals. Okay. Excuse me. All right, so that's kind of what I have here, and we'll start seeing these values pop up a lot. So those same values you were seeing alpha over 2 pop up for confidence intervals a lot, those are going to be the same values that pop up a lot for two-tailed tests. And then the one-tailed test values will be a little bit different than confidence intervals, but we'll start seeing these same 3 values a lot because we're always going to be kind of using these same benchmark alphas or type 1 errors that we're setting. I kind of already mentioned this, for the right-tailed test, it becomes a little bit difficult because you can't just look up alpha. If you just look up alpha, you have to remember you found the right value, but you need it to be positive. Right? So that's what this is kind of referring to. I think it's just easier for me to kind of work it out by hand. Here's kind of a nice little summary. For a left-tailed test, I'll have this, and notice here, I've been notating this as the critical value that gives me alpha in the tail. This is just reminding us that critical value is just like a cutoff Z value. Maybe that's an easier way to reference it, right? It's a cutoff Z value that gives you alpha total in your tail for a left-tailed test. Here they're positive critical values for a right-tailed test, and then a pair of critical values and a reminder that it's the values that give you alpha over 2 in each tail with a total of alpha in the tails. Okay. All right, so I think let's try to work through an actual problem. I think this will help. We'll kind of end on working through maybe, we might get through 2 problems here. So our steps to the critical value approach is we'll still have to figure out what the null and alternative are. Do we have a left, right, two-tailed test? In order to find our critical value, we still need alpha, right? Using alpha, find your critical value. And here, step 3 and 4 are going to be interchangeable. Doesn't really matter what order. So find your critical value, and if it helps kind of draw out where that rejection region's at, then find out what your test statistic is based off of, I have sample mean here, or off your sample proportion. Plot that test statistic. If it's in your rejection region, you can reject. If it's not, you fail to reject. Okay. So kind of similar to what we're doing with the p-value approach, just instead of using our test statistic to find the p-value, we use alpha to find our critical value. So let's go through something with some actual numbers, and we'll kind of work through these steps. So let's suppose you want to test the hypothesis for whether or not more than 50% of the population owns a gun. Actually, do I have this one set up right? Let me look through this real quick. Okay, yeah, this is one where I'm going to show you something kind of interesting. All right. So we want to test. Come on, here we go. We want to test for whether or not more than 50% of the population owns a gun. So what we're thinking about is our alternative hypothesis is that this true proportion, population proportion, is greater than 0.5. So we'll assume the opposite is true, which is that it's less than or equal to 0.5. Okay. I then take a sample of 100 households, so my sample size is 100. I find a sample proportion of 0.41. Okay. Well, we've already identified the null alternative hypothesis here, right? Which is, so we've got B. So what type of tailed test do we have? Careful, what sign is in my alternative? Greater than, so I've got a greater than or a right tailed test. Okay. Because only evidence to the right of 0.5 is going to go against my null, right? It's going to be the only evidence for which I could reject the null. So we got a right-tailed test. But here, if I simply at this point just asked, do you reject or fail to reject the null, what should you know the answer is? You don't even have to work this one out. Or actually, no, sorry. More than 50%, a recent. Oh, I think I. Oh, yeah, no, I'm right, sorry. I was looking at these wrong. Why do you already know the decision of this test? If I look at the sample proportion I found, does it go against my null hypothesis? No, it actually supports it. So I'm not going to reject it. However, I'm just going to show you, you could actually work through this and you would still end up not rejecting your null. So common sense says, I found a sample proportion that supports the null, I'm not going to reject it. But even if I'm like, I don't know, miss that and work through the whole problem, we'll end up at a point where we see we clearly don't reject it, okay? So next step, what are our critical values? And let's do the 1, 5, and 10% significance levels. So I could look all these up kind of quickly. But if I have a right-tailed test, which of these do I know have to be, which of these can I rule out? For a right-tailed test, I know the critical values have to be, yeah, on the right-hand side of the standard normal distribution, those are positive values. So right away, I know it's A or C here. Now I can look them up. I'll kind of do it quickly for you, or actually show you kind of a shortcut that we use with confidence intervals. So I don't think I had it open because I wasn't sure if we would get this far. So let's go down. Because I didn't think I was going to need these. So there we go. Let's open the t-table real quick. Remember, we said the last row of the student t-table gives us the standard normal distribution values. So it becomes really helpful to use this student t-table to look up my standard normal values in this last row. So what do I want? I wanted alphas of 0.1, 0.05, and 0.01. So it's going to be these three columns. So I go down to that last row to get my standard normal values, approximately 1.282, 1.645, 2.326. I can actually get them out to the third decimal if I do it this way. Now, the other way, I'd have to go through and look up, hunt down, find where 0.1 is, write that z value down, find where 0.05 is. Now, I'll get close, right? But I'll have to kind of round to that second decimal. So either way is fine to find those critical values, but that's, saves a little bit of time if we use the student t distribution to find them. So we've got our critical values now. If we wanted to kind of think about what this is going to look like, I'm going to really draw exaggerated too, so this won't be to scale. So 2.33, here's my rejection region. And remember, this corresponded to the 1% significance level. 1.65, this corresponded to the 5% level. Like I said, this is not drawn to scale. I know I'm getting close to the mean here. And then here's my rejection region for the 10% level, which would be 1 point. So here's my three critical values, and I've got my rejection regions drawn. The next thing I need is my test statistic. Okay. So what's my test statistic for this equation? Well, or equation, problem. Well, I'm going to have to go down here and remember that for my sample proportion, I took the sample proportion minus the assumed true proportion and then divided by the assumed true proportion times 1 minus that assumed true proportion over the sample size. So my sample proportion I found 0.51, assumed true proportion was 0.5, and my sample size was 100. I'm just going to go ahead and plug these guys in. Okay. So I think that was negative 1.8. Okay. So now I've got this test statistic. What I'm going to, and actually, what did I forget to do right here? I drew this as a left-tailed test. Why did I do that? Because I wasn't thinking. Okay, we have our test statistic. Let's redraw our critical value regions because I apparently completely forgot what we were doing. So I actually want these to be over here, right? So 2.3, 3, 1.65, and then 1.29, and these were the 10, 5, and 1% significance levels. Can't believe you guys let me get away with that and didn't stop me. All right. That makes a little more sense for a right-tailed test, right? Okay. So just to be clear, I drew this wrong because I was thinking about a left-tailed test and didn't realize I wasn't writing out negative values, so I apologize for that. So we've got our right-tailed test critical values and rejection regions. We've got our test statistic of negative 1.8. I'm going to plot my test statistic here. Is that anywhere close to my rejection regions? No, it's not even the right sign, right? And this makes sense because just looking at it, it was something that supported the null. So there was no way I should be even close to rejecting it, right? Another way to kind of think about this is we also said if the visual, if you don't, we don't have to use the visual, but this is one case in which the visual helps because I said to always think about it as if the absolute value of my test statistic is greater than my absolute value of my critical value. Well, using that approach only works if it's evidence that goes against the null. So kind of like your first check should always be, does my sample value even go against the null? Because if it doesn't, I already know what my rejection decision is going to be, right? I know that if I found something that supports the null, I'm going to fail to reject it. And sure enough, if I work it out, that test statistic is nowhere near my rejection regions. Okay. Any questions on that? I know this one's a little bit, I was kind of using it to kind of show you that, even if we work through the whole test for these ones that are easy, we could still come up with the same decision. Now, maybe what's a more interesting, so here, it's not in my rejection region, so we kind of fail to reject. I'll use a different color here. What is a more interesting example would be, let's say I work something out and I find maybe here, instead of 0.41, I found 0.59, and it ends up being the same test statistic, but it was kind of like right here, 1.8. So let's say instead that was my test statistic. What levels could I reject at? Well, it's in my rejection region for the 5% level. It's in my rejection region at the 10% level, but not in the rejection region at the 1% level. So I could kind of only reject at that 10 and 5% level here. Okay. That would be a more interesting test statistic, right? This one's not very interesting. Okay, so what we're going to start out with on Thursday, work through a few more proportion and critical value examples. I'm then going to show you a little bit in Excel, just for those of you who it might help clarify or kind of make sense. You'll see it in Excel on Thursday. You're not going to have to do anything in Excel for hypothesis testing until far after the exam. But just in case that helps some people learn, I want to introduce that. We'll also finish the very last thing of hypothesis testing, which is what happens if we don't know the population variance. Similar to confidence intervals, we might have to use that student t-distribution, okay? All right, so we've got that Excel assignment that's due at the end of the week. I will tell you right now, I know my schedule Friday is going to be busy. So if you have questions on Friday, I cannot promise I'm going to get back to you after like 2 o'clock. So start working that early. So if you do have questions, you can get those to me kind of here the next couple days, okay? Also, there will be an online quiz today that's due before we meet on class Thursday. Just kind of probably having you practice a few of these problems, okay? All right, enjoy this beautiful weather, and I'll see you on Thursday.